Welcome to Ultimate Sleep Doctor. Tonight, we'll be journeying into a realm of astonishing precision. Deep within laboratories, a silent marvel ticks away, unaffected by the fleeting rhythms of our world. These are atomic clocks, instruments that measure time with the unwavering stability of atoms themselves. They are, in essence, tiny universes of incredible constancy. Consider the vastness of space, the relentless dance of celestial bodies. Our own world is simply a smaller, more intricate reflection of this profound order. It's a beautiful reminder that even in moments of quiet, there's a steady, predictable force at play. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe. Let your thoughts drift like clouds across a still sky. Let's begin. Let's begin our journey into the heart of time itself, starting with a remarkable element called cesium. Cesium is a soft, silvery white metal, and it holds a secret that allows us to measure time with incredible precision. But it isn't just any cesium, it's a specific isotope, cesium-133. This isotope is particularly special because it behaves in a way that's perfect for our needs. It's not constantly jiggling and vibrating like many other atoms. Instead, it possesses a remarkably stable energy state, a state where its electrons are locked into a particular orbit around the atom's nucleus. This stability stems from the fact that cesium-133 has a very low energy level. To get to this lower energy state, the electrons need to absorb a specific amount of energy, a precise amount of electromagnetic radiation. This absorption triggers a transition, a movement of an electron from a higher energy level to that stable, lower energy level. It's a quantum phenomenon, meaning it's governed by the strange rules of the very small. Now consider the atom itself. It's made up of a central nucleus containing protons and neutrons surrounded by orbiting electrons. Electrons don't just whiz around randomly. They exist in defined energy levels, like steps on a staircase. Each step represents a possible energy state for the electron. The lowest step is the most stable, and it's where we find cesium-133's electrons. The key to the atomic clock lies in the frequency of these transitions. When an electron jumps down to a lower energy level, it immediately emits a photon, a tiny packet of light energy. The energy of this photon is precisely related to the frequency of the light, and more importantly, the frequency of this emitted light is constant. It doesn't speed up or slow down, no matter what. It's an incredibly reliable signal. The cesium-133 atom, therefore, acts as a kind of perfectly tuned radio. Scientists shine a beam of microwaves, a form of electromagnetic radiation, onto the cesium atoms. These microwaves have a specific frequency. If that frequency matches the natural frequency of the electron transitions in the cesium-133, the atoms will absorb the microwaves and re-emit them at the same frequency. This repeated absorption and re-emission creates a very stable and consistent electromagnetic signal. Scientists can measure this frequency with extraordinary accuracy. It's this precisely measured frequency that forms the basis of the atomic clock, a clock that's far more accurate than any mechanical clock, and far more stable than relying on the movement of a pendulum or the rotation of the Earth. It's a truly remarkable demonstration of the predictable behavior of matter, at its most fundamental level. Before the steady tick of cesium atoms became synonymous with perfect time, the quest for precise clocks began with something much older, the humble pendulum. For centuries, humans observed the rhythmic swing of a suspended weight and realized it was governed by a predictable, repeating pattern. This was the first clue that time itself might be measurable, not just perceived. Early clocks, dating back to the 16th century, utilized these swings, relying on the consistent fall of objects under gravity. These early pendulum clocks, often beautifully crafted with intricate designs, were a significant improvement over relying on sundials or the human body's rhythms. They weren't accurate by today's standards, of course. The length of the pendulum had to be carefully calibrated to match the time of year, as the gravitational force itself changes slightly due to the Earth's orbit. As clock-making techniques advanced, so did the desire for greater precision. Clockmakers began experimenting with different materials for the pendulum. Brass, steel, and even silver were tried to minimize friction and ensure the smoothest possible swing. The problem remained. Even the most carefully constructed pendulums were still susceptible to external disturbances. A slight breeze, a bump, or even temperature fluctuations could cause the swing to deviate, introducing errors into the timekeeping. The 18th and 19th centuries saw a surge in clock-making innovation, driven partly by the demands of navigation. Sailors needed accurate time to determine their position at sea, and this spurred the development of marine chronometers, incredibly precise clocks designed to operate reliably on ships. John Harrison, a brilliant English clockmaker, is particularly famous for his work. He spent decades designing and building a series of large, complex clocks, culminating in the H4, which was the first chronometer to consistently maintain accuracy during long sea voyages. Harrison's clocks were revolutionary because they incorporated numerous refinements to minimize the effects of motion and temperature. However, these mechanical clocks, despite their improvements, were fundamentally limited by their reliance on mechanical movement. The inherent imperfections in materials, the inevitable accumulation of wear and tear, and the susceptibility to external forces meant that they could never achieve the truly stable and predictable timekeeping needed for certain applications, like radio transmission. Scientists and engineers began to look for ways to create clocks that relied on physical processes that were, themselves, incredibly stable and unaffected by external influences. The search had begun for a clock based not on movement, but on the fundamental properties of matter and energy. The story of the atomic clock doesn't simply appear. It's the result of a dedicated pursuit, a slow but relentless gathering of knowledge and experimental data. At the heart of this story are two brilliant physicists, Joseph Oswald Hansrud and William Francis Lawrence Oppenheimer, working at Bell Telephone Laboratories in the late 1930s. They weren't trying to build a clock in the traditional sense, not one with gears and springs, but rather a way to measure time with unprecedented accuracy, based on the incredibly stable nature of a single atom. Hansrud, a young engineer with a deep interest in precision measurement, had been studying the behavior of rubidium atoms, focusing on their tendency to absorb microwave radiation at a very specific frequency. He realized that if they could precisely control and measure this absorption, they could create a remarkably consistent timekeeping device. Oppenheimer, a seasoned physicist with a particular fascination for atomic spectra, brought his expertise to the project, recognizing the potential significance of Hansrud's initial observations. Their initial experiments involved using a vacuum tube to cool rubidium atoms down to incredibly low temperatures, colder than outer space. This was crucial because the cooler the atoms, the less they would jiggle and vibrate, making their atomic transitions, the absorption of microwave radiation, much more predictable. They constructed a complex apparatus, meticulously shielding it from any external vibrations or electromagnetic interference. This isolation was absolutely key to their success. The team's fundamental breakthrough came with the development of a cell, a small, sealed chamber containing the cooled rubidium vapor. Within this cell, they introduced microwaves, carefully tuned to match the natural frequency at which rubidium atoms would absorb radiation. By precisely measuring the amount of microwave energy absorbed, they could determine the frequency of the atomic transition, a property that remained stubbornly constant regardless of temperature, pressure, or even the position of the Earth. Crucially, they recognized that the frequency of this absorption wasn't just a random occurrence. It was tied to the exact energy level of the rubidium atom. And because the energy levels of atoms are determined by their fundamental structure, they are, in principle, unchanging. This presented the core of their invention, a system based on a single, incredibly stable atomic transition. The early prototypes were far from perfect, of course. The initial instruments were bulky and sensitive to environmental fluctuations. However, the team's meticulous data collection and persistent refinement of the apparatus steadily improved the accuracy of their timekeeping. They recognized that the key wasn't simply measuring the microwave absorption, but rather understanding and compensating for all the factors that could potentially influence it. By 1949, Hansrud and Oppenheimer had successfully built a cesium clock, a slightly modified version of their rubidium system that was significantly more stable and accurate. This cesium clock demonstrated the true potential of atomic timekeeping, setting the stage for the development of the incredibly precise clocks that we rely on today, clocks that allow us to navigate the globe, communicate across continents, and even explore the mysteries of the universe. The heart of the atomic clock's remarkable accuracy isn't simply about the cesium atom itself, but about what that atom does. It's about a precisely defined way of counting regular events, a fundamental unit of time. This unit is called the hertz. Now, hertz might sound complicated, but it's really quite straightforward. It's simply a measurement of cycles per second. Let's break that down. A cycle refers to one complete oscillation, one full up and down movement of the cesium atom's energy levels as it transitions between its two energy states. Think of it like a child repeatedly bouncing a ball. Each bounce is one cycle. The more times the ball bounces in a second, the higher the number of cycles per second. The Hertz value then describes exactly how many of those cycles happen. For the cesium clock, the standard is 9,192,630,1770 Hertz. That means the cesium atom is oscillating 9,192,630,1770 1,770 times per second. But why this particular number? It wasn't chosen randomly. It arose from meticulous measurements made by the National Bureau of Standards, now NIST in the United States, working closely with scientists in other countries. They needed a value that was incredibly stable, something that wouldn't drift or change over time. They selected this specific frequency because it was based on a precisely defined transition between two energy levels of the cesium-133 atom. The choice of cesium-133 itself is crucial. It's an isotope, meaning it has a specific number of neutrons in its nucleus, making it particularly stable and predictable. This stability ensures that the atomic transition remains consistent, providing a dependable marker for time. The frequency isn't just about the atom oscillating, it's about the regularity of that oscillation. This 9,192,630,1770 Hz value serves as the international standard for time. Every other time standard around the world is ultimately defined in terms of this frequency. It's like a universal language for time, allowing scientists and engineers to synchronize clocks and coordinate activities across vast distances. Consider the implications. Without this stable frequency, global navigation systems like GPS wouldn't work. The satellites orbiting Earth rely on incredibly accurate time signals to determine their position. Similarly, financial transactions, telecommunications, and scientific research all depend on the precision provided by the atomic clock and its fundamental unit, the Hertz. It represents a cornerstone of modern technology, ensuring accuracy at a scale that's truly awe-inspiring. The beauty of the system is its inherent stability. The cesium atom, being incredibly stable, provides an extremely reliable tick, a constant, unwavering reference for time, allowing us to measure the universe itself with remarkable precision. The precision achieved by a single cesium clock, as we've seen, is remarkable. But the universe isn't a tidy, predictable place. Earth itself is spinning a little unevenly, wobbling on its axis, experiencing variations in its rotation speed due to the gravitational pull of the sun and moon. These changes are incredibly subtle, measured in milliseconds per century, but they accumulate over time and would throw off any single clock attempting to maintain absolute accuracy. To address this, scientists realized they needed a coordinated system, a way to constantly monitor and correct for these irregularities. This led to the development of International Atomic Time, or TIE. TIE isn't based on the workings of just one clock, but rather a vast, interconnected network. Hundreds of highly precise atomic clocks, primarily cesium fountain clocks, are strategically placed around the globe. These clocks aren't just sitting quietly, they are constantly exchanging information. Each clock meticulously measures the frequency of the cesium radiation they're using to define time. The clocks are located in places with different environmental conditions, some in mountainous regions to account for variations in gravitational pull, others in areas with significant atmospheric disturbances. This diverse placement allows the network to capture a much more complete picture of Earth's rotation. Think of it like a global orchestra, each instrument, each atomic clock, contributing to a harmonious whole. The data from these clocks is continuously transmitted to a central time and frequency standard located in Paris, France. This central facility, operated by the International Bureau of Weights and Measures, analyzes the incoming data and makes minute adjustments to the TIE scale. It's a continuous feedback loop, constantly correcting for the Earth's movements. The adjustments aren't done randomly. they're based on sophisticated models of Earth's rotation, developed through years of observation and data analysis. These models take into account not just the variations in the Earth's rotation, but also the influence of solar activity and other factors. The goal is to produce a time scale that is as accurate as possible, representing the actual movement of the Earth through space. It's important to understand that TAI isn't intended to be a clock in the traditional sense. It's a reference time scale, a benchmark against which all other time measurements are compared. It's the foundation upon which all other time scales, like Coordinated Universal Time, UTC, are built. UTC, which is what you likely see on your watch or phone, is derived from TAI and is adjusted to account for daylight saving time in different regions. The ongoing maintenance of TAI relies on the dedication of scientists and engineers worldwide, continuously monitoring and refining the system. It's a testament to humanity's ability to understand and interact with the most fundamental aspects of the universe, time and space. The network represents a remarkable achievement in collaborative scientific endeavor, ensuring the accurate measurement of time across the planet. The story of incredibly precise timekeeping didn't end with the cesium clock. Scientists, ever driven by the desire for even greater accuracy, began exploring alternative atomic oscillators. These weren't simply about measuring regular vibrations. They were about harnessing the most stable and predictable ways a nucleus could resonate. The cesium clock, while revolutionary, had limitations in terms of size and cost, and researchers sought ways to achieve similar performance with more compact and potentially cheaper instruments. One significant development emerged with the rubidium atomic clock. Rubidium-87 is a radioactive isotope, meaning its nucleus is constantly decaying. This decay, and the energy released during it, creates a remarkably consistent frequency. Unlike the cesium clock, which relies on the absorption and emission of photons, the rubidium clock utilizes the microwave radiation produced when these excited rubidium atoms return to their ground state. The frequency of this emitted radiation, around 688.286 MHz, is exceptionally stable. Rubidium clocks are now commonplace, finding applications in GPS satellites, telecommunications networks, and scientific research. They are particularly well-suited for use in environments where space constraints or cost are major considerations. Another fascinating advancement involved the hydrogen maser. This device employs a beam of hydrogen ions, electrically charged atoms, traveling through a specially designed tube. When these ions are accelerated, they collide with the walls of the tube, creating a cascading effect that generates microwaves. The frequency of these microwaves is determined by the mass and velocity of the hydrogen ions. What makes the hydrogen maser so extraordinary is the exceptional stability of its frequency. The hydrogen ion's motion is incredibly predictable, minimizing any external influences that might cause variations. The key difference between the hydrogen maser and the rubidium clock lies in the mechanism of frequency generation. Rubidium relies on atomic transitions after excitation, while the hydrogen maser uses the kinetic energy of moving charged particles. Both technologies represent distinct approaches to achieving ultra-stable frequencies. These clocks are generally more complex to build and operate than rubidium clocks, demanding precise temperature control and shielding to isolate them from external vibrations and electromagnetic interference. Furthermore, variations within each technology exist. Different designs of hydrogen masers utilize varying ion velocities and tube geometries, each tweaked to optimize frequency stability. Similarly, rubidium clocks employ different resonator designs, the structure that amplifies the microwave signal, to further refine their performance. The ongoing research and development surrounding these atomic clocks continues to push the boundaries of time measurement, constantly improving accuracy and paving the way for even more sophisticated applications in science and technology. The seemingly simple act of counting atomic vibrations holds the key to understanding and coordinating our world with unprecedented precision. The precision of an atomic clock isn't just a fascinating scientific achievement. It's a vital tool quietly shaping our world in countless ways. Its incredibly stable frequency, far more consistent than any pendulum or quartz crystal, finds applications across a surprising range of fields. Let's start with navigation, a domain where even the smallest discrepancy can have significant consequences. Global Positioning System, GPS. Satellites rely entirely on the accurate time signals beamed down from atomic clocks located here on Earth. Each satellite carries a highly accurate clock, constantly transmitting its time to GPS receivers in cars, ships, and smartphones. These receivers, in turn, use the time difference between the satellite signal and their own local time to calculate their precise position on the planet, a feat of geometry powered by atomic time. The longer the distance between the receiver and the satellite, the greater the time difference, and therefore the more accurate the position fix. Beyond GPS, atomic clocks play a crucial role in modern telecommunications. The transmission of data, whether it's a phone call across the country or a video streamed around the world, relies on incredibly precise timing. Networks utilize the consistent frequency from atomic clocks to synchronize their equipment. Think about the complex digital signals that make up a telephone conversation. These signals need to be carefully aligned in time, and an atomic clock provides that foundational accuracy. Similarly, high-speed internet data transfer, the packets of information that form the basis of everything we do online, also depends on precise synchronization, again thanks to the stability of atomic clocks. The impact of atomic clocks extends deeply into the realm of scientific research. Physicists use them to test fundamental theories about the universe. For instance, changes in the rate of cesium clocks have been meticulously measured over decades, providing evidence for time dilation, a concept predicted by Einstein's theory of relativity. Scientists also employ atomic clocks in experiments exploring gravitational waves, ripples in spacetime predicted by Einstein. The incredibly sensitive detection of these waves requires an exceptionally stable time reference, provided by the precise tick of an atomic clock. Furthermore, atomic clocks are essential in fields like geodesy, the science of measuring the Earth's shape and gravity field, and in paleoclimatology, where they are used to date geological events with unparalleled accuracy. Researchers analyze variations in the frequency of atomic clocks to reconstruct past climate conditions, looking for subtle shifts that reveal information about ancient temperatures, sea levels, and ice ages. The accuracy achieved with these instruments is truly remarkable, offering invaluable insights into Earth's long history. It's a testament to how a tool designed for fundamental science has become an indispensable part of our technologically advanced world. The current generation of atomic clocks, marvels of precision built on the vibrations of cesium and hydrogen, are already unbelievably accurate, routinely measuring time to within a second over billions of years. But scientists aren't resting on these remarkable achievements. They're peering deeper into the very fabric of reality, exploring ways to redefine what we understand about time itself, and it's leading to something truly extraordinary: quantum clocks. These new clocks aren't based on the predictable oscillations of atoms, but on the bizarre quantum world where particles can exist in multiple states simultaneously. Scientists are investigating the behavior of trapped ions, individual atoms held in place by electromagnetic fields, and their incredibly sensitive response to microwave radiation. The key is that the energy levels of these ions, when precisely controlled, exhibit quantum properties that are far more stable and predictable than those of traditional atomic clocks. One particularly exciting area of research involves utilizing superconducting circuits cooled to near absolute zero. These circuits, when manipulated with exquisitely controlled pulses of electricity, behave like tiny, quantum harvesters, constantly drawing energy from the vacuum of space, a concept rooted in quantum mechanics known as the zero-point field. The precise timing of these energy fluctuations is being explored as a new basis for timekeeping. But the ambition doesn't stop at simply building more accurate clocks. Scientists are beginning to question the fundamental nature of time itself. The current view, based on Einstein's theory of relativity, describes time as being interwoven with space, forming a four-dimensional, space-time continuum. However, quantum mechanics suggests that time may not be a fixed, absolute quantity. Experiments using quantum clocks are beginning to hint at the possibility that time is not uniform across the universe. Gravitational effects, predicted by Einstein, can actually distort space-time. Clocks in stronger, gravitational fields will tick slightly slower than clocks in weaker fields, a phenomenon known as gravitational time dilation. Furthermore, research into entanglement, where two particles become linked in such a way that they share the same fate no matter how far apart they are, presents another potential avenue. Some theoretical physicists propose that maintaining entanglement could create a temporal link, a way to potentially transmit information across time, though this remains highly speculative and faces enormous technological hurdles. These future quantum clocks are not just about measuring time more accurately. They represent a fundamental shift in our understanding. They could allow us to test general relativity with unprecedented precision, observe the subtle effects of space-time curvature, and perhaps even, one day, unlock secrets about the very beginning of the universe and the nature of existence itself. It's a truly breathtaking prospect, and a reminder that science is a constant journey of discovery, pushing the boundaries of our knowledge with each tick of the clock. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. We've journeyed through the intricate dance of the atomic clock, its steady tick a testament to precision and timelessness. Now, let your thoughts drift, calm and unhurried, as the world around you softly stills. Allow yourself to surrender to the quiet to find your own sanctuary of rest. Good night.